Bon dia, good morning. This is a pleasure to open this third module of the School of Advanced Studies on Water and Society Under Change. And it's a pleasure to receive Professor Dimitri Solomatine, first time in our University of São Paulo in São Carlos campus, also being followed through a network, an alliance with two campuses in the Northeast Brazil, Federal University of Pernambuco in Recife City, and Federal University of Campina Grande in Campina Grande City, Paraíba. So we are 3 states attending to this lecture in person and in distance. So the students have the opportunity to interact with the mentors and the professors. And of course, we have a week of lectures and also a specific guidelines to follow the material. So for me, Professor Solomatine is a good pleasure, and I would like to thank Maria Clara Fava also for her warm attendance and also the logistics and the success of this lecture and this course is also with you. Thank you very much. And also for the students and also for the supervisors who permitted their students to attend this lecture. So thank you very much and great success. Thank you.
Thank you very much. Well, to answer to your warm welcome, I would like to thank Professor Mendiondo for inviting me, Maria Clara Fava for arranging this, because due to her visit to Delft, actually I think this happening is actually taking place. So she spent, what, almost a year?
8 months.
8 months in Delft, in the Netherlands. So we work together on interesting research projects, together with Professor Mendiondo at a distance, and now we all come together perhaps to advance our research and education even further. And I would like to thank your university also to arranging this, your government that is paying for this. CAPES, so that's important. So governments work, as we can see, so no complaints about governments anymore. They give money for education and research. Right, and I would also like to welcome the participants from away from northeast of Brazil. How long is it from here? I don't know. 1,000 kilometers?
2.5 hours in plane, through plane.
2.5 hours in plane, so it's around 2,000 kilometers, I suppose. So warm welcome to everybody, to all audience.
Thank you.
Right, so we can start now the boring part. It was fun, and now the boring part, the lectures. Then you need a chair. Sometimes I will have a seat so that it's easier to operate the computer.
Okay. I bring the glass of water.
A glass of vodka, you said?
Yes.
That's okay. Yeah, not too much. No, vodka, you said? Water. Okay, yes. I would like also to welcome this person who is missing. Maybe it's a very important person, brother. So I'm not sure who is this person, maybe a minister or deputy minister who would come later, I understand, right? Okay, so who am I?
Just a minute. You have a free USB or the pointer?
Yes, I have a USB for the pointer. Just a moment. So let me look at the escape. And where is the light? This? Yeah. Good. Okay. It works. Great. Oh, that works. So right. Can you hear me? Do I need to use microphone? Yes? For Skype?
Yeah.
Okay. So I'll try. First question, audience. How much do you know about water, about engineering, hydroinformatics, modeling, neural networks, numerical methods? You're master students, right? So you went through bachelor studies. So you should know all this, I suppose, or at least part of it. I see some question on your faces. Okay, we'll see how it goes. Second question, I have sent to you the links to downloads. Have you downloaded the stuff? Okay, then today in the morning I sent the links to more presentations. So you can follow them and take notes if you wish. I will tell you the file name. They are numbered from 0 to 3, I think, to 4 now. And there will be perhaps 1 or 2 more presentations to follow. Now, in these presentations, we will not attend all the slides. There are hundreds of slides. But I thought always when I give these lectures, I give longer presentations so that later you can also comprehend more material than only during this lecture. It always helps. And of course, I will tell you if we're skipping some of the slides. But most of them we will attend. So prepare for hard work. We have in total 7 lectures, 2 hours each. We have breaks of 45 minutes. Sorry, breaks of 15 minutes. Lecture 45, then break 15. So it's will go like this. But sorry, I forgot to introduce myself. So I'm Dimitri Solomatine. You can pronounce it Solomatine or Solomatine as you wish. I'm Russian by origin, so if you speak Russian, we could communicate much easier than, but I don't speak Portuguese. So perhaps your Russian is much better than my Portuguese. Yeah, obrigado, this I know, but not much more. So I am from the institute which is called IHE Delft Institute for Water Education, also known as UNESCO IHE. For many years we sort of had this name, but now we're slightly changed our status in relation to UNESCO, but we're still category 2 institute of UNESCO. So today I heard from Professor Mendiondo that we will have sort of more public lecture in this room. So that's why my introduction would be shorter than I have planned initially, because more introduction would come during the lecture in the afternoon, so it will be a bit of illogical move back, but I think you will be able to follow this. So let me see. So this is more or less contents of the course. You have it. So this presentation is called Opening Brazil. I think it's called like this. It has number 0. I'm by training computer scientist, so I count everything from 0. You know, this is difference between engineers and computer scientists, that computer scientists count from 0 because arrays and C start from 0. Anyway.
But we have computer science students.
And who is this? Okay, good. So you will answer all the questions concerning computer science. Now I know. Okay, good. We'll have also several exercises. We'll see how it goes and how much we will be able to get into this exercise. It depends on the pace of the lectures. But I also send you the exercise. You can do it yourself because it's quite detailed account of... Okay, good. Connected?
Yeah.
Shall I repeat everything now?
No, they are watching you on YouTube.
Oh, okay, good. Right, exercises. So we'll try to do some of the exercises because it helps. So we will, first I will have brief introduction to hydroinformatics, but also I'll do it after lunch for wider audience. We'll look at basics of modeling theory. If you get bored and you say, we'll know all this, tell me, we just skip this material, no problem. We'll introduce notion of optimization and some of the important notions, because what I find, many civil engineering students do not have optimization courses, and the notion of optimization is very important, in my view, in water management, which is not very well developed yet. We will then look at some of the machine learning technologies for data-driven modeling, so it's yet another paradigm of modeling, and I will present you some of the examples of research projects that are done by our staff or master or PhD students coming from different countries. And I will tell you a bit more about our education at IHE, to misusing this opportunity to advertise our institute. So hydroinformatics is a term coined by Professor Michael Abbott, who is also author of the book Computational Hydraulics. So those who do computational hydraulics know this book. It was translated to a number of languages. It was published in the 60s and then in the 70s, and latest edition was in the 90s, I think. So he realized that advances in numerical methods were already so much in the end of the 80s, and a lot has been implemented in software, that it's time to connect to information technology. So he coined this term, hydroinformatics. So informatics is he writes in his book, it's a Russian term, but I doubt it because it comes from informatique in French, so it's perhaps this combination. But indeed, in Russian, informatics is called informatika, and maybe it would be called in Latin if it would have existed, I'm not sure. But hydro is clear, it's water. So bioinformatics, geoinformatics, hydroinformatics, it's one of these areas that developed at the interface between two sciences. One is water science, another one is information and communication and computer science. This is the building of IHE, which I made from the window of my office in winter. And he started hydroinformatics in this building. That's an old building in Delft, so if you're in Delft, I can tell you the history of this building. Napoleon had lunch in this building in 1810 when he visited his brother. Anyway, quite an old building, and you're very welcome. So, successor of Michael Abbott was Professor Roland Price, who initiated the software line in Wallingford Software, which is called now Innovize. So HydroWorks, InfoWorks, first codes were written by Professor Price in England, in Wallingford, and he continued to develop hydroinformatics further. So we define hydroinformatics as, let me switch to display settings, which would be duplicate like this. Yeah, so it's easier to read. We define it as a study of the flow of information and the generation of knowledge. So you see, generation of knowledge is important, and we'll talk about it in a second. Related to the dynamics of water in the real world, through the integration of modeling, information technologies, and artificial intelligence. Also taking into account sustainability and social implications, that's an important thing, because society needs technologies to develop better. And then why we're doing this? We do this for decision support and smart management of water-based systems. So management is critical here because we want to manage our water better. Natural waters, but also man-made or woman-made, human-made. Now we should be politically correct. You cannot say man-made systems because women also building systems, so should we say human-made systems? For water management. So what we do, we integrate data, models, and people. So let me skip a couple of slides for the afternoon. So international recognition of hydroinformatics has come, I think. There are conferences, books published, special issues, Society of Hydroinformatics in different countries, and so on. Now, this is an important slide to understand what we do, actually. So we start with data. Always, if we want to manage something or change something, we have to first collect data about this system. So data about water is collected by traditional gauging, remote sensing gauging, but also by humans. It's called citizen observatories. So Maria Clara on Friday, I think, will tell us more about citizen observatory, right? Because she will be defending her PhD. So this is the center of knowledge in Brazil, I suppose, in citizen observatories. So she was sitting on the roof of this house and observing the floods, and then somehow this information by communication systems is coming to models and used, assimilated, right? So that's how it was. Now, this data should be brought in. So if, let me say something. If we are solving the problem of, for example, flood management, let's be a bit more concrete. Of flood management. So we need data. Then we need hydrological load. So we run our numerical weather prediction models, which run atmospheric models forward in time. So it means we're making predictions. So that's very important. And then we feed this hydrological load into our hydrological and hydraulic systems, hydraulic models, which would then generate future states of environment in terms of water flows, water levels, and so on. Now, all this is coming to these people. So modeling results is actually new data. That's why if you look on top, we say we use data to build models, and we use models to generate knowledge. So models encapsulate knowledge developed by many scientists and engineers during many years. So models are generators of knowledge. It's not only data. That's important to understand. And then decisions. So in this picture, there are 3 persons in front of old computer. Who is the manager here? Who is making decisions, do you think? One in the suit. Okay. So it's not the person who is in front of the computer. So these people, that's a correct answer, but let me continue for a second. So the person is an analyst. So this person runs sophisticated software, but I'm afraid many managers wouldn't know what is on the screen. Also, public wouldn't understand what is on the screen. It's dangerous to tell the public that your house would be flooded. Immediately, price of the houses would go down. You know, real estate agents would be unhappy, commit suicides, and all this. So we don't like that. But I think the manager here is this woman here to the left, also in a sort of suit. You know why? Because man is the head. You know, man is the head. And woman is the neck. And neck turns the head whichever direction she likes. You know. So perhaps the woman is the manager. Sorry, I should be careful with this sensitive joke, so I would withdraw my joke, so you never heard it. Anyway, apart from jokes, that's important that these people would be making decisions about water management here. They would maybe open some dikes or tell people to evacuate if flood is coming, and so on and so on. So a lot of management decisions where humans' lives depend on this flow of information. So we talk about flow of information from data to models to knowledge to decisions and then impacts, because decisions always have impact on something. So that's holistic approach in hydromathematics that we follow. Let me quickly show you a quick example of a hydroinformatics system, which is GLOFAS. It's a global flood awareness system. So what I did a day ago, let me try to, or maybe you can go to internet, type in the code, which is in the presentation. I don't see it, however. So this is Latin America, you see in Africa. So I zoomed in. It was day before yesterday, before I traveled. So I tried to understand if we'll have to take umbrella or not with me. And these are forecasts, global forecasts generated in real time, every 6 hours, and maybe even more often in particular places, generated in UK and in Italy by Joint Research Center, working together with ECMWF, which is European Center, ECMWF, European Center for Medium-Term Forecasting. And on top of it, they run hydrological models that would show you, here you can see current surface water. So they will show you not only weather forecasts, they will also show you hydrological forecasts. There is Liz flood model, global model, running in the background on the supercomputers and showing you where possible alerts should be issued. Okay? So this system is not terribly accurate because it's a global model, but it gives you awareness of flooding. So you may think, aha, something is going on. So what people then do, they would use this global model to run local models, using global models as boundary conditions to feed into their local model. So if you want to calculate something around San Carlos here, you would have to run local atmospheric models here, and then you can more accurately calculate what would be with the low flows in this particular area. Why this? We call it also hydroinformatics system, because it takes the data also from remote sensing, it takes data from gauges and so on. It runs the models then forward in time, atmospheric models, and then it runs also forward in time, hydrological models. Decisions are not here, it's purely information system. Decisions are to be made by managers, so it's not here. It's up to you what decisions to make, but you can choose from different sources of data which is coming from different research centers. Okay, so that's the same thing, but just a different thing. So you can go to this address, globalfloods.eu, GLOFAS forecasting, and you can run it yourself for any area in the world and choose the time lag and all this. Right, I want to say now, to introduce some of the topics that we'll be doing. The word optimization. So what is optimization, do you think? Have you heard this word? So what are you optimizing in your life? Money, good. What else? Time, okay. Health, important. Yes. And these criteria are conflicting, actually. Often, if you have more money, you not necessarily have more health, because you start worrying about your money and you see, oh, where to invest, or I may lose, or whatever. Or you don't have enough time, then you have, cannot do much. Anyway, optimization is an important principle of hydroinformatics, and we will talk a bit more about different applications of optimization, but mainly I want to introduce you to the principles of this. And you want to optimize, for example, urban networks for urban drainage, because they work in a non-optimal fashion. We want to optimize reservoir operation, because a lot depends on how much water would you discharge at a certain moment in time during a year, because multi-purpose reservoirs also not only used to generate electrical power, but also to do many other things. We allocate resources between different users, like water resources, but also money resources, and so on and so on. And also we calibrate models. We'll talk about this more. Okay, artificial intelligence. We'll have a big block about this, so I will not talk too much about this. But important to understand that artificial intelligence, what you read in the press, in fact, actually a bit more sophisticated stuff than statistics. So, and that's why we call them data-driven models. So we build data-driven models using this data that we collect, and then the model may be used per se, or it may be used together with hydrological model. As I demonstrate, we'll discuss this. This is called hybrid model, when two models work together. So artificial intelligence model, this model would predict errors of the physically based models and then will generate improved forecasts. So that's what we will discuss. Okay, let me skip this for the afternoon. So in this course, we will use MS Excel for basic data analysis. Okay, that's a simple thing, just to introduce you to the subject. We'll use a simple hydrological model that we wrote at IHE for educational purposes, but we can play with it and see a bit. Have you used hydrological models actually before? Computer scientists maybe didn't, but other students, hydrological models? What models did you use?
I use the high mode model. It's a
High mode. Yes, and others? No? SWOT? Okay, others? Swim? Okay. But this one is much simpler than SWOT and SWIM. It's quite simple model, tank model, but it allows you to play with data, and actually it's quite accurate for simple cases. So you can use it, and it's a gift to you if you want to. You wouldn't be able to do real consultancy, but to educational. Then we would use a couple of software using for computational intelligence, using Veka package and neural machine. And then if we have time, we'll use also Globe, which is optimization tool to calibrate tank model. And you can use Gmail to send messages home, how boring this course is and all this stuff, so that's for sure. So objective for this course would be to introduce some basic notions and techniques in hydroinformatics, to raise your interest using modern tools for solving water-related problems. So again, this course cannot teach you everything. It more opens windows, as we say, not Microsoft windows, but real windows, to look at different things over here. So, and also to point to possible interesting topics in your future career, because hydroinformatics opens really opportunities to do interesting stuff, which was not done before. Why? Because it connects to sciences. Okay, I will talk about IHE and hydroinformatics after lunch. So let's get started. Any questions so far? No? So on 14th of December 1963, there was a flood in California. So I would like to show you a movie now, because it's always fun. It wasn't fun for the people who were there, but let's see. And sound, where is the sound? There is no sound? What happened? Why there is no sound? And you see sound is okay, yeah? Look. Ah, it's not through HDMI? No? Ah, sound is here, from this side. No, where is my...
No,
oh,
no,
sorry.
no,
I'm
it's
sorry.
not sound.
It's okay.
It's
Oh,
not
there.
sound, it's over there.
Yeah, I forgot.
This is microphone.
I hope so. No, I don't hear anything. Ah, this is VGA, so VGA blocks, so it should go here, but you don't have a cable here. Okay. No, HDMI, but it becomes VGA. You see, there's no sound here. Oh, here, maybe this one, right?
This one, yes.
Let's move on, that's okay.
Aqui mais perto, João.
Yes, okay, sound.
Station KTLA arrived.
Okay, so colleagues, think you are in 1963, you're watching television. This is what you see. It was the first flood televised on American television and maybe around the world. That's what you see.
Oh, yeah.
So what is my screen? Sorry.
Is the blue line 9?
I see everything here.
So, again?
Again, you said Windows P?
P. And again? This one? Yes, this one.
Right, okay. So then...
Evacuation began. Camera crews. Shortly after the evacuation began, camera crews from TV station KTLA arrived at the reservoir and began to broadcast live aerial pictures of a disaster.
So this is the dam reservoir to the left and people living to the right of this dam there. And you can see the dam starts to break. This is the beginning.
In the making.
And right here now, as we come up over the Baldwin Hills Reservoir, we can see the main break in the reservoir itself. The reservoir.
While workers desperately tried to repair the breach, water began to flood the streets below. As the LAPD continued to evacuate the valley, the leak in the dam's face became a torrent.
There goes a large chunk of the inner cement here in the Baldwin Hills Reservoir. That hole is 50 feet across.
For the first time in American history, aerial pictures of a disaster were being broadcast live on television. At 3:38 p.m., just 4 hours after the first sign of trouble, the Baldwin Hills Dam gave way.
It was no sign on original movie, yeah. But it will come back. So you see how much power water brings, enormous energy. It has to be released somewhere. So how to model this? You see cars, trees, houses. What?
Within 2 hours, the flood had passed, leaving behind a trail of devastation and a thick coating of mud. Due largely to the fast action of local and state officials, only 5 people were killed by the failure of the Baldwin Hills Dam, including one woman who drowned when her car was swept into an excavation hole. Early investigations into the dam's failure focused on faulty construction or seismic activity as possible causes. Authorities eventually focused not on the dam itself.
And we'll never know what authorities were focused on, because movie stops here from YouTube. So you have seen many of these movies perhaps during last years on television when floods happen and they destroy human lives and property and so on. Now, why I'm showing this one? So Brett Sanders in University of California built a model to replicate this event. Microphone, thank you. But you just stand up and come and hit me, and then I will do things, you know, because otherwise I... So why to build a model of this event? The model is built, first, of course, curiosity. This is what drives researchers, you know. You think they do research to help people? No, that's just pure curiosity and fun. That's why we do research. But second is to see if your model can replicate an event which was quite well recorded, because water levels were known. From this footage, you can calculate the velocity of water. You know the topographic map more or less at that moment. So you can have quite enough data to calibrate your model. So it's very useful to do it in other cases as well. So now I'll show you what model of Brett Sanders shows. So this is Baldwin Bridge. Let me start again. You see, it shows the event. And what was found, in fact, if you compare to this footage, this model was calibrated well enough to replicate more or less, not 100% accuracy, to replicate the event. So that's one of the uses of model that you can see here, is not to predict something, but to do post-mortem analysis, so to say, to replicate events which happened in the past, but then it would allow you to forecast what may happen in the future when you use this model. Also, it serves as a learning tool. You learn a lot in the modeling technology when you apply this. You teach your students, they would go to the field, they would go to other places where such models have to be built, but they already know how to build such models through these examples. So it's one of the examples of using two-dimensional modeling. You can use also three-dimensional modeling if needed, but this 2D model, which would replicate quite well the known event. It's a hydrodynamic model. If you want to know more, get to the link. There is a link to Brett Sanders' web pages, and you can also download his software, which he wrote together with colleagues for 2D modeling, when we use it sometimes in our studies. Okay, again, lottery. If I press Shift F5, let me go to duplicate slideshow. Right, good. So the link is here, Sanders Engineering UCI, Brezo. Brezo is the name of the model. You can find enough information here. Now, when we look at catastrophic events like this, at floods, which is very often the subject of applying our newest technologies. Why? Because floods create a lot of damages. Thank you. She is coming to hit me, so I immediately try to obey and take the microphone. We look at this. So can you model all this by simple equations, Sun-Venan equations, which assume rectangular channels and whatever, you know, simple flows? No. Because look, there's debris flow, which is very difficult to model. There are cars. They may block flow of water and so on. Here, dam break. You see very complex phenomenon, which is dam break, and it floods, and then it further floods. So what I want to say that simple models is indeed only introduction to modeling. But when you apply the models, you have to realize complexities of applying the model in real life. So never expect that your model, which is written by researchers in their nice offices, using differential equations, would replicate all the complexity of real world. Now, what about uncertainty in modeling? So uncertainty was not really taken into account for many years because the training and also the practice was based on deterministic approach. So assumption was that humans are so clever that they would write equations that would replicate natural phenomena. And these equations work with real numbers, and equations then would generate also real numbers when solved, and real numbers would show you, for example, this is a forecast of the discharge. This dashed line is the deterministic forecast given to you by the model. So we run an atmospheric model, then we feed the data about rainfall and temperature into our hydrological models, and then we get this deterministic forecast. But for the managers, it's a bit of a problem, because if alarm level is the red line, and you can see, even I have here a wonderful pointer, you can see that red line, so the forecasted water, forecasted flow does not reach the alarm level. So evacuate or not? Maybe not, because this is what rule says. But if you assume certain uncertainty in modeling outputs, so that you say, okay, at any given moment, the range of output would be between blue and red line, so there would be interval of outputs. Then you don't know, because this interval intersects with this red level. So it creates uncertainty also in decision making. And people don't want to go to jail if they say, no, here, don't evacuate, and water level suddenly reaches this upper limit, which was predicted, and then people are killed, and so that's a problem. So managers like to work with deterministic forecast because they have rules which they have to follow, and if you bring them output in the form of intervals or PDFs, probability density functions, then they get nervous. However, this is reality. So what I want to say is that models are uncertain, data is highly uncertain, rating curves are inaccurate, which you use, because this is discharge. And discharge is not often measured, it's calculated based on water levels. So water levels, high water levels are not observed very often, so you don't have enough data to train a rating curve. So your discharge measurements, so-called measurements in your archive, are not accurate. So how can you calibrate model on inaccurate data? So it creates a lot of uncertainties. We'll talk about this later as well. So we discussed this. So we, in hydroinformatics again, we integrate information communication technologies where we bring in data, use analytical tool to work with this data, and then maybe assess the uncertainties, and then bring to models and generate new data, new knowledge. Let me skip this slide. So again, returning to this slide, what you see here is the figure from Mike Shea model, which was developed originally by universities, but then Danish Hydraulic Institute in the 80s and 90s took over and developed them to a sophisticated tool which integrates hydrological surface models, groundwater models, and hydraulic models here, rivers. So Mike 11 would run here, you see rivers are here, and then groundwater component of Mike Shea would also. So this is integrated model. So that's a current trend, which was already for 15 years maybe, to build up integrated models that would take into account water flows, and not only water flows actually, also wind, and atmospheric load and solar radiation and so on, to integrate all of it in complex models. Disadvantage of this is that you need expertise to run all these components in practically one human, which is not always possible to find these people. So problem is not only the models themselves, which you can buy, but also the training of personnel that would be able to run them. So we have many participants coming to our institute to be trained from developing countries, and there is a very big problem that people come to be trained and then they change jobs. So they want to hire, these water authorities hire new people, they want again change jobs, and this is a problem also. So it's not only modeling problem, it's also human problem. So that's what also we all have to think about. So again, what is the place of modeling in the whole decision-making process? So if you want to solve a certain problem, you pose objectives, you acquire information, you analyze this information, maybe archive, you build databases and such like, knowledge bases. Only then you do the modeling. So that's important, and maybe one of the most important parts, you have to pose objective. Why are you doing this? Often people say, oh, let's build some model, look at it and do something. But the modeling depends very much what do you want to achieve, target audience and so on. Okay, then when you apply modeling, you make decisions, you get feedback on this, evaluate impact, and then you redo things again because you will change and so on and so on. So that's infinite process, decision making, and role of modeling. So role of modeling is then to supply you with new knowledge about the future states of the natural processes. So how do we encapsulate knowledge related to water? In hydroinformatics, we try to think of several components here. So one is tacit or implicit knowledge embedded within a person. So that's what you know. That's very important. Second is words printed and stored in electronic media. These are books, papers, and instructions and guidelines, and so on and so on. But then, this is what we think should be made part of all this, mathematical models. All these formulas, algorithms, are encapsulated nowadays in software, and then contain actually often much more than books. Because books present you the theory and maybe experience, some examples, okay, that's all fine, but mathematical models allow you to create virtual world, feeding in new data. If new data comes in, you create a new world, virtual, in a computer memory, and then you run this world forward, predicting what the world would look like in a day or 10 days or in a year. So that's why mathematical models form the important part of the knowledge base which you use in making decisions. So, and it should be also organizationally recognized. Often in an organization you have library where you store books, you have some managers and all this, but mathematical modeling is not given enough attention, unfortunately. Why? Because managers were not trained to use models still. So that's also important to realize when you're building up new organizations for water management, to ensure that you have enough resources put in here. In large projects done by large companies, it's recognized actually, and they realize if they invest 1% of the project budget into proper modeling, they will get savings of 10% or more. Or without models, they simply cannot implement the project. So when large infrastructure projects are built, for example, in Europe, but also in Brazil, I'm sure, you do environmental impact study, studying how the new infrastructure would influence environment. How can you do it without models? You cannot. So you have to create this virtual world of tomorrow to evaluate the impacts. So that's what you do. So when we integrate all this and humans coming in, we would have a hydroinformatics system. That's what we want to call hydroinformatics system. Okay, I already talked about integration of models. Okay, this example showing that you, in fact, have global numerical weather prediction models. Here it says 100 kilometers grid cell, but now it's much lower, much smaller, because this slide is 10 years old. So every 3 years we decrease the cell size, and now it reaches, even for global models, only 2 or 4 kilometers. And then you run local models here on the basis of global models. You run local models where you have grid sizes up to hundreds of meters. So perhaps, for example, WRF model, which is free to use, is run in many places in Brazil as well. Your Met Office also runs a global model along with United States and England and China and Russia and Brazil also running global models, especially calibrated for region of Latin America, of course. And then for each region you can run local models. So this integration is important. Modeling now. So this is a model. It's called physical model or scale model in hydraulics. So you would build up of concrete or plastic, meandering river, and would try to understand how the flows develop if you put some vegetation or build a bridge, or there is sedimentation coming in, and so on and so on. So you build scale models, and it allows you to replicate future infrastructural work. Well, it's expensive because you need human involvement, and it's not terribly accurate. So for the last 30 years, we moved to computer-based models where we could imitate this virtual world by running the models, which are, say, this is 2D or even 3D model, and here you can see there would be a vertex, or perhaps sediment would be brought in, and sedimentation would be happening here. So what's happening here? The model is run forward. Every second a frame is made, and there are random particles thrown into the computer memory, and they follow the flow. And here you can see, for the manager, it would be great if you go to the manager with this picture, you know, you can get promoted quickly, because it's your final objective, of course. It's not to save rivers from sedimentation. You want to get, you said money, your professor said, so you want to raise in salary, so you get promoted if you show these pictures. So please use visualization tools to make your point. Well, it's of course a joke, but indeed, for managers who cannot read more than half a page, you know, your reports are typically not read. Nobody reads them. Be aware of this. Only executive summary is read. But if you show a movie and you're in a room, they have to watch it. And indeed, it says much more than 1,000 words. So that's very important option. It sort of looks like a movie, but in fact, it carries a lot of information over here. So this equation, don't show it. Of course, you should show that you're a clever person. Oh, you know, mathematics, you know. To impress, to create complex of inferiority, but then you have to take it back and show this, and people say, ah, yes, yes, we do this or we do that. Okay, so this is also a model, as you can see. So we collected a lot of data. This is data-driven model. We want to find the trend in this data. And this line is based on this cloud of data. So instead of using this cloud of data, we can use only this line. And this is data-driven model. We'll talk about it more in a minute. And this is also a model. What is this model? Computer scientists? Huh? You said you're from computer science.
Yes, yes. We usually use like functions instead of just
Oh, but this is entity relationship diagram model, which shows the relationship between several data entities or information entities, which is farmer owns field and has a crop. These are attributes of the farmer: field name, farmer name, farmer address, and all this. These attributes of the field, the attribute of the crop, attributes of the ownership relationship, and all this. So it's also a model of information relatedness between different components of information world here. It's called entity relationship diagram, also a model. So if you're thinking of building a database where you would store your data, also have to study a bit how to build databases in a proper way. For this, you may come to IHE, and we'll teach you if you want, but okay, it's nothing. Right. So we will not use scale models in this course of lectures. We will look at this model, not at this one, we have no time, but we will look at this. Sorry, yes, question? Okay.
the name of the diagram?
Previous one, this one?
No, the model.
This?
Yes.
Entity relationship. So these are entities. Farmer is an entity. So it's a notion, entity, right? It has many records. As you have 100 farmers, you have many records in the database.
One question.
Yes?
Why some people call them business model?
What? The?
Business action model.
Business, yeah, I don't know. So it's a business talk, you know. People want to publish books, so they invent new names.
Computer science sometimes.
Yes, we have a modeling the business process, so the activities carry out to execute something, and this one is more for database.
Yeah. Yeah, that's right. Sorry, I withdraw my statement about business talk. Indeed, for workflows, but business model is very wide term, whatever you call. But indeed, for processes, you use different graphical language. This language doesn't show dynamics, it shows statics. So, and if information flows between farmers and fields and all this, then you will use another language, indeed. But it's called entity-relationship model, or ER model. So, I have 1 minute before the break. What is a model? Model is a simplified description of reality. Is it description of reality, this model? This is a graphical model. Look at this. What reality does it reflect? Does it exist in reality, this thing?
No.
You see, but I can draw it. You see, if you look, follow this part, you would understand it cannot exist in 3D world, but in 2D world it exists. So you have to try to avoid the thing when you would be building a model of something that doesn't exist. Your model works well, you can show it to people and say, look, nice model, shadows, colors, wow. Impossible, however, in real world. So it's important that model indeed is description of reality, of not of something else. Then we can also say it's encapsulation of knowledge about a certain mental or physical or social process. Encapsulation of knowledge in a model, often simplified. Model is always simplified. Now goals, first to understand the study system or domain, that's useful, but it's not enough. But also we use the model to predict the future. And we can often say we build hydrological model, but if it's not predictive model, what's the use of it? Okay, you understand a bit better how flows flow, you know, water flows, but typically you would aim at predictive model, forecasting models. And then, of course, goal of modeling is to use the results of modeling to make decisions. It's not part of modeling, it's beyond, but when you build a model and you do modeling, you have to understand what decisions would be made. If decision is made about sedimentation, then your hydrodynamic model is not enough. You have to put in sediment there and so on and so on. So you have to also make the type of a model function of your decision making. Okay. Right. The break? Good. Thank you. Any questions before we continue? My question, where is the coffee actually? Here. Excellent.